For Q&A, as always, we're using Slido platform. So to ask your questions, please go to slido.com and enter ESIG22 as an event code. The instructions are also currently posted in the chat and on the screen in the front slide right now. We plan to save 10 minutes for Q&A at the end, and then we'll wrap up at the top of the hour. An email with a link will be provided once the video file has been posted, and we also plan to provide short responses to all unanswered questions after the webinar. So if you have any questions, please don't be afraid to ask your question in Slido. Also, if you see a question that is similar to yours, please feel free to vote them up, and this way we can prioritize the questions that have been submitted. Just to introduce the webinar today, you probably have seen recent updates to grid code enabling and to new grid codes enabling grid forming operations, and they open kind of opportunities for a multitude of applications. This in turn has exposed a gap between component level controls and complete grid code compliant plant level solutions. This presentation will highlight additional requirements and considerations to convert a collection of subcomponents into plant level solutions that are compliant with the latest grid code requirements for grid forming operations. I would like to welcome today's presenter, Ben Braun, who is a principal engineer for TSO UltraStack applications at Fluence, where he leads the qualification process of converter suppliers, grid forming controls, and software integration thereof. Over the last 10 years, he has designed in-house grid forming controls applications and detailed multiple integration studies for grid operators. He received his Bachelor of Science degree from Rose-Hulman Institute of Technology in the US and his Master of Science from BTU Cottbus in Germany. Again, just a short reminder to use Slido for your questions with the event code of ESIG22 to ask your questions. And without any further ado, please, Ben, go ahead and get started.
Thank you very much, Julia, for the introduction, and thank you to ESIG in general for the opportunity to present. It was just about a month and a half ago when I presented in person at my first ESIG conference. A lot of these slides and the content is largely similar, but of course now we have a broader audience and we have a little bit more time for some direct Q&A sessions. So if you were in those in-person sessions in Arizona, you're already one step up on everyone else. Feel free to ask plenty of questions. I'm going to start sharing my slides and we can get going. Okay, so as the principal engineer for power system controls at Fluence, it's been my job now for 3 years to kind of wade through the ever-changing landscape of grid forming applications, grid forming requirements, and how to put that all together and ultimately design and build projects for our customers that we know are going to stand the test of time and also do exactly what's required of them. Over that time, and also over my time at previous companies, there has been quite an evolution of the applications of grid forming. Very early on, you had a lot of isolated cases. There were some industrial black start projects that were really just only grid forming for a very brief moment in time. 99% of the time, they're just grid following on the grid, maybe doing some arbitrage or some frequency response. And if everything hits the fan and you have a blackout, then of course it would have to spring into life and restore critical systems, either it be maybe a hospital or IT infrastructure or just production facilities. Now the nice thing or the convenient thing about these types of projects was that you had a very heavy hand in shaping the process and the sequence. You know, you could quickly disconnect the POI, get rid of the external grid and anything that's happening there, and you knew more or less what was going on in your facility, your balance of plant, and you could turn on loads selectively, and so all of the sizing you could really do for this very specific niche case. And because of that, a lot of the power conversion system suppliers or inverter-based resources, as they like to say in America more so, the IBRs or the PCS, even with a little bit of basic grid forming capability, they could more or less get the job done. Then, somewhat in parallel, but as the success of grid forming controls grew and grew over the last a decade or so, you started to see a lot of isolated cases. People like to call these microgrids. Nowadays, they're in the double, even triple megawatt scale. So that's by no means micro in my book. So I prefer to call them isolated systems rather than microgrids. Most of those were with grid forming droop. You were looking at getting more renewables in the grid, turning off N-1 must run thermal generation to really save fuel, save emissions, save the bottom line for the final ratepayer. And you started getting more and more needs. So these systems now, they needed to be able to handle many more unexpected events. You had this wild grid outside of the point of interconnection of the battery, and you didn't always know what was going to happen. So you had to plan for a lot of different contingency events. And then we started to see that, okay, not all of our converter suppliers have the grid forming capabilities that we need for such applications. And as time has progressed and as more and more renewables have come on the grid, we start to see that even in mainland or continental or large scale bulk power systems, the amount of renewable penetration that we're seeing, non-synchronous penetration, is so high that even these systems are now in need of something to support either the voltage and or the frequency or both. And they need to do so in a way that is faster and more robust than grid following solutions, which we've used so far. And again, we saw that the capabilities of our PCS suppliers, fewer and fewer could actually offer these types of capabilities. So just to start with that as kind of a brief look backwards in time, how we've got to where we are today. You on the call, you might be more interested in the industrial black start or the isolated systems or the on-grid systems. All of what I have to say, I think, is fairly applicable to all of these use cases. Of course, the large systems are getting more and more press and more attention today. And as grid codes start to evolve, they have the ability first to even be built. But beyond just battery energy storage systems, some of the lessons learned and the considerations that I'm going to highlight in this presentation, they do have some parallels to wind or PV. Of course, these are very different technologies with their own unique considerations that suppliers have to look at if they want to do grid forming with those assets. But there are some similarities, and I'll try to touch on those from time to time. So regardless of whichever application you want to build your power plant for, you need to know what are the actual codes and requirements. And I like to start from the top down. That's oftentimes the easiest. So what are the grid codes in different regions? Is there even a grid code in your region? Is it a hard requirement or is it a voluntary requirement / recommendation? The fun thing about this slide is that you see how a lot of these different regions that have published codes or voluntary requirements or recommendations, that there's a lot of cross-linking and referencing going on. And I think that's great because especially me as a solution provider, the more harmonization and the more consistency across the globe, the much more easier it is to design a product that can serve as many markets as possible. I like to joke that we absolutely do not need a UL version of grid forming and an IEC version of grid forming. At the end of the day, what grid forming is really trying to get at is mimicking the physics of a synchronous generator, and those physics they don't know any sort of regional norm boundaries or anything like that. On this slide, you'll see that some of these documents are grayed. That's because they're a little bit anticipated, or they're still, from our point of view, sort of in a draft working phase. We've heard recently that ERCOT and MISO are planning to release something this year. Terna has an appendix to their grid code which mentions grid forming requirements for batteries, but what they actually mean in detail is still a work in process. Where we definitely see the most definitive requirements is in the UK. They were one of the first movers, but then very quickly Finland, Australia, Hawaii, and slowly but surely also Europe, where ENSO-E is driving a working group right now to get the grid forming requirements defined, which then the national TSOs in Europe can implement into their regional codes. What's missing here, and what I wrote at the bottom, is that there's still no IEC or UL or IEEE standard that actually specifies the requirements or the means for testing grid forming capabilities. The 2800 from IEEE does address it, and I think there's a lot of good talking points in there, but it stops short from actually defining requirements. And the same for anything in UL and IEC. There's some very minor mention of maybe standalone inverters or something like that, but it's definitely not to the point where you can just as a solution provider or as a project developer, that you could just go around shopping for inverters or power converters as you would in a grid following project and say, right, I need to see this certification and this one, and if you've got that, then I know you're fit for function. Unfortunately for grid forming, that does not yet exist. On top of the technical grid code requirements to even get connected, you also have to understand, how is this thing going to make money, or why am I building these new complex but also really cool features into this system? Is it because I'm getting compensated for it, as is the case in the Stability Pathfinder 2 initiative from National Grid ESO? There they opened a tender. They said, look, we have identified points in our grid that are weak, and they're going to get weaker over time. We need to support those. We know that grid forming technology has gotten to a fairly mature state, and they themselves also released a grid code defining how to quantify that grid forming capability. So they said, right, if you're a battery, you're grid forming, you can help strengthen our grid. You can also design your plant to participate in other services, energy arbitrage, frequency response, voltage response. Those are all open for you. And from that, tell us what it would cost, and we'll see whether we sign up for a contract with you or not. In the end, a couple of synchronous condensers won contracts, but also 5 grid forming batteries won, and the first of those are being built and going online this year. So very exciting. We're going to start seeing this on a grander scale, and also with some market-based procurement. Because of the mechanisms there, different customers had different bidding strategies. You could see 2 of the batteries that won, they bid purely with short circuit level capabilities, so really voltage strength by providing fault current, and zero inertia. Whereas 3 of the other batteries that won, they bid both for short circuit level and inertia. So you could see that already based on the market mechanism, the grid code, it allowed you to offer one or the other, and to customize your provision of both SCL, short circuit level, and inertia. And you had different project developers doing their homework, crunching their numbers, and coming with different ratios. So it's kind of exciting to see how the market, when you give your developers some freedom, they can come up with different solutions. On the other extreme of that, both market-wise and geographically, you have in Australia, you have now a system strength charge. Basically, this says as a renewable plant or as a battery, as a non-synchronous generator, you are not supporting system strength. You're even, in a way, consuming system strength. And in order to run the grid reliably, AMO or the local TSOs, they need to somehow procure equipment to ensure that that stability and that system strength is guaranteed. That costs them money so that you can get on their grid and make money. So it seems fair to say that maybe you should have to pay a system strength charge for that. This has led a lot of project developers to say, I would like to avoid that, right? Any project developer, they're building power plants to make money, also for good causes. But the only way you can really scale good causes is if they're economic. So the very surefire way to not only avoid consuming system strength, but actually providing system strength is jumping from away from grid following controls and moving to grid forming controls. Now, AMO and the local TSOs, they're not saying for your system strength that you have to provide a certain level of short circuit level or a certain amount of megawatt seconds, as was detailed in the National Grid Stability Pathfinder 2 tender. They simply say kind of do no harm. There is some more formulaic ways to quantify it, but you're not really incentivized to overbuild for these services. You just have to make sure that you can reliably connect, stably connect to lower short circuit ratio grids. And then you have somewhere in the middle what's coming about from the ENSO-E initiative that I mentioned in the previous slide. It first came RFG 2.0. There was something called the requirements for generators, and initially that was all, stood on its own, but now we have an RFG 2.0 drafted first at a higher level, at the ACER level, which was then passed down to ENSO-E, which is then being worked out with through an expert working group. There's going to be a implementation guidance document, which then is transmitted to the national levels, where they then convert it into code with some individual adjustments for their specific needs. What's interesting about that is, contrary to National Grid in the UK or AMO down in Australia, they were very focused on voltage stability. It's not that ENSO or the European grid is not focused on voltage stability, but one of the bigger driving factors is actually inertia. They still want to use grid forming controls to get to it. Of course, there's still going to be locations where they need voltage stability, and over the next years, it's only become more and more. But right now, Europe is having more of a inertia issue than voltage stability. And so because of that, there's a regulatory agency in Germany called the Bundesnetzagentur. They released a paper where they're actually promoting the creation of a kind of a bonus scheme. So before the RFG 2.0 comes into place, which at the bottom of the slide here, there's a rough timeline shown. It's going to be about 3 years after all of those documents are published before there's really a compel aspect from the codes for new projects. In between, we already see an inertia shortfall, and so if you are ready today or tomorrow in the near future to provide that, we're going to put together a scheme that you can actually get compensated for that. So 3 different market mechanisms, of course, 3 different grid codes, or if you take ENSO-E, then you can split it into multiple different grid codes. But at the end of the day, in order to design your system, as a good engineer, you have to start, what are my system requirements? System requirements can be purely technical, but then they can also be techno-economic. That's what this slide gets at. And finally, maybe after all of that, you can start to say, okay, I think I know what I actually want to do with my battery power plant. And just to give you an idea of what Fluence has been doing with grid forming over the years, you'll see a collection of projects here. A fair amount of them are already built and in operation, about 500 MVA worth of grid forming projects already online. And we have another 1,500 MVA contracted, so in detailed design, construction, some of them already in commissioning, going online soon. Of all of those sites, there is a bit of diversity in terms of the energy duration. So you see some with 1 hour, some with 2 hours. Uh, there's even some requests for more and more energy duration, because what we're seeing is that people want to tap into these grid forming revenue streams or services, but as battery prices are coming down and as other, let's say, traditional battery markets are slowly potentially becoming saturated, uh, the developers and the project operators are looking for new revenue streams, and the revenues are coming more and more from energy business. So pairing of high duration energy projects with the highly dynamic and short-term um, transient capabilities of a grid forming control, that's really that's a match made in heaven, so to say. Underneath all of these projects are some sort of internal classifications in terms of what it's actually doing. So we had the Black Start projects, but then is Black Start the same as just backup, where you're not starting a generator, but you are securing a load? Okay, those are technically two different applications, very closely related, yes, but slightly different. You can have a co-located Black Start versus an external Black Start somewhere else in the grid. Again, similar, but nevertheless uh, different enough that we have to approach them in different manners. Um, Down in Australia, the grid forming system strength, that was one where we have to promote the stability of the grid, as particularly connecting to low short circuit ratio points. Uh, some of them, Mortlake Lake, for example, also providing black start service. This is different than the Statkraft project in the UK, where it was actually designed and built for a very specific short circuit level that has a direct contract with National Grid to provide. So you see that even from those three applications that I started with early on, you can start to kind of create more and more sub applications, and it can start to get a little bit messy. But nevertheless, if there's enough of a difference in the application, it is worthwhile to treat it as such. So now we get into a little bit more details on the actual plant design. Of course, the power converter, the inverter, is a huge part of any grid forming plant or any grid following plant. But there is currently, from conferences and talking to various suppliers and customers, there does seem to be an impression that grid forming is only about the inverter. It's only about the inverter controls. But if you jump back to that previous slide where I was highlighting all of the different sub applications, you start to realize that, well, in order to really optimally provide one of these applications versus the other, it's not enough to only look at my inverter. I have to look holistically at the entire plant. Um, you know, protection considerations. If my inverter is now a voltage source rather than a current source, if it's maybe even providing a heightened amount of fault current, I have to make sure that while providing that to the grid if it needs it, I also still protect my own internal equipment if I happen to have a fault somewhere. Um, how do I combine these new highly transient grid forming capabilities with the old traditional applications that a battery energy storage project would be contracted for? Let's say I'm trying to do arbitrage and I'm supposed to be charging or discharging depending on the price, and suddenly a rock-off event occurs, which which causes an inertial response. How? Oh, just a second. I need to. Apologies there. I've got a bit of a cold, so needed to cough for a bit. So how do I combine all of these um, services on top of each other without fighting? And then on the plant side, um, is my meter at my point of connection, is this still sufficient? Is it still fast enough? Is it recording all of the metrics that I need? My plant controls, do they know how to handle all of this dynamic power of the grid forming controls? If I'm doing black start or if I'm providing a very critical service to the grid, are there potentially new cybersecurity aspects that I have to look into? Even within black start, there's sub applications of black start that I'll get into later. On your auxiliary system, it's not just that the PCS has to survive an HVRT or an LVRT, your auxiliary system does as well. And what about if you're now providing a much higher amount of reactive power to the grid? That's also going to impact. Apologies, I already drank my glass of water, so I have to try to make it through here. I'm going to jump to the next slide. So while there are other aspects to consider on the holistic plant level, of course, as I said earlier, the PCS is a very vital part of this. And unfortunately, there are still no component level standards that we can design to, or that we can test to, that we can validate to. So all of that still has to happen in-house right now. Fluence has been doing this for many, many years. Previously, one of our founding members, Siemens, already had their own grid forming controls, their own grid forming product with the C storage inverter. So there is a fair amount of knowledge there, but nonetheless, every inverter supplier is approaching this in a slightly different manner. In order to really be certain that they can do what they say they can do, you have to go through a very strenuous number of steps to validate these suppliers. And some of them might make it through all the way to the end, and you can use them for all of your applications, all of your projects. Others might not be fully there, and you can maybe only use them, for example, for a black start or for a isolated use case. But definitely the first step is due diligence on your documentation. If you say you can do it, you have to have it documented. You have to say how you do it. I don't need to know all of your IP, but I need to know on a high level how you do it. I need to know what happens when you don't do it, if something goes wrong, how to handle fault situations, how to size it, as I'll get into in a later slide. You need to have your documentation. If that's not there, you don't even have a foot in the door. Part of documentation are validated models, not just RMS, also EMT models. So we're looking there then mainly for PSCAD or Power Factory, PSSE, and then any number of Hill platforms, so that we can also do some hardware in the loop testing. Going forward, once you've ticked all of these boxes, all right, let's go to your facilities. Let's see your test bench. Let's see how you perform with the real system, performing effectively kind of a type test for your grid forming controls. If you pass that stage, then we're going to start bringing you into our own lab setting. Some of that is physical inverters with batteries. A lot of it is, of course, just on a hardware in the loop system. How does our power plant controller, what we call our FOS, how do we need to adapt that to cohesively work together with your grid forming controls? And then finally, at some stage in this whole process, we gain enough confidence where we say, right, this inverter, it does what it says it can do. We're ready to sell it. We're going to start offering that to our customers. They're going to start putting this on the ground, and ultimately, of course, we have to follow it through to project execution and on into the service phase to make sure that even despite all of this due diligence, some issues can still arise. And the most important thing is that you stay on top of that and you learn from any lessons and surprises along the way. So on the inverter, uh, looking at the hardware side, because a lot of focus of grid forming is really on the controls side. In this slide, I like to put together a couple of example topologies of common inverters that are on the market right now. Of course, you can go into even more topologies that are coming out. DC-DC converters are becoming more common, moving away from IGBTs and going to silicon carbide switching. That will have big implications for the industry. But just looking at sort of what's really already on the day and what the vast majority of batteries, PV and wind are using. Of course, PV and wind, then you don't have batteries behind it. But you have four main topologies here. All of them can be utilized for grid forming projects, but they have special considerations. So on the top left, very straightforward, single winding, single grid forming controller. It has multiple power stacks in it, but they're synchronized, and you got a single DC bus. Okay, for your overall plant design and even in a grid following project, of course, there's still many factors to consider. But in terms of grid forming controls, it's pretty convenient because you've got one voltage controller behind its impedance from its own transformer. It's galvanically isolated from any of the others. The risk of circulating current it's non-existent. You could still have some oscillations with other systems, but because of that impedance, you're pretty safe. Moving to the top right, effectively the same thing, but using a 3-winding transformer. You just have to take care that you don't or that you spec it properly so you don't have too much coupling on those two low voltage windings there. The bottom row is where it starts to get a little bit more complicated and you have to pay more attention. So multi-DC buses, these are very common in battery systems, also in PV systems. It can be quite nice to separate your DC bus into smaller chunks, but then you open the risk for more common mode voltage, more circulating current. And if you want to run grid forming on such a system, the controls that you have to have of each of those four systems, as it's drawn here, has to be much tighter to avoid running into circulation current issues. The bottom right, similar to the bottom left, but these are actually 3 different PCS. They're sharing a low voltage winding. They're not synchronized. So not only do they have the multi DC buses, but you also have multi controllers that you have to try to send commands to as simultaneously as possible. And there your risk for circulating current grows even more. So yes, grid forming controls is about the inverter, not only. And yes, grid forming controls are about the controls, but not only. Also, the hardware is playing a very important aspect. Continuing on the thread of hardware, what we see, rightfully so, from customers is that they expect, if I have a inverter that can do this much power in grid following, I expect that in grid forming it can do the exact same amount of power, right? Why not? The reason why not is because by shifting from the current control mode where the inverter controls can very precisely limit and protect their own hardware, going from that to a voltage control mode where you're just in the first instance serving whatever the grid needs. This is a paradigm shift. And in order to do that, and to do that safely, and for a manufacturer to say, yes, you can do it, and I don't have to have any concern about my hardware failing and then getting into warranty issues, many of those suppliers will say, right, in grid forming, you actually have to derate the amount of power capability you can do. Effectively, that creates a headroom for their controls, as shown here in the top right, very conservative, kind of qualitative. I try to always make my slides very agnostic, not calling out any specific manufacturers, because the industry is evolving. It's evolving at a rapid pace. Things are changing. So we're only talking about concepts and theories, and not really honing in on any specific values. But so in the top right, some suppliers will be very conservative. Maybe it's their first actual project with grid forming, and they're going to say, look, when you turn on grid forming, you don't get the same amount of steady state power. I need quite a lot of headroom there. You get some that will say, yeah, I can give you something, and you know what, I can even give you a little bit more on top for a brief time, um, for some fault current, or maybe for a brief spurt of active power for an angle jump, or for a rock off event. And then you have the more complex, but potentially the more beneficial, a bit of a trade-off, where they say, right, if you give me a bit of headroom on your plant sizing, so effectively derating your PCS, your inverters, or overbuilding them to derate them, uh, when you actually need the short circuit current, or the overpower for inertia, I can give you so much more than if you wouldn't have overbuilt me. So, uh, not a concrete example, but if you overbuild by 10%, I can give you 50% overcurrent for a short time, versus if you don't overbuild, I can only give you 10%. So ultimately, economically, it starts to trade off, in particular for the transient services that grid forming controls provide. Um, we don't need fault current for multiple seconds. Maybe in some isolated grids, they push us to 3 seconds or so, but generally we're talking about hundreds of milliseconds. On inertia, if your grid is near to nominal frequency, and you suffer an event which causes a large rock off, there's only a few seconds before that rock off has driven your frequency so far down or up that all generators start to trip or fall offline. So these type of grid forming aspects, whether it's more voltage stability related with the short circuit level, or frequency stability related with inertia um, and angle jump power, these are very, very transient things, and you can either size them with a blunt steady state manner, or you can try to be a little bit more complex and follow this trade-off down at the bottom right. So that's been the focus on the inverter, but now coming back up to that holistic view again, what is the role of a plant controller? So a power plant controller, PPC, what is its job? If the inverter is in grid forming and it's doing all of these great things, it's holding frequency and voltage, why do I even need a PPC? Well, in many ways, the role of the PPC becomes even more important. As I said, you have a paradigm shift from the current control to the voltage control. In the current control, the PPC tells an inverter to do something and it does it. And it tells another inverter to do something and it does it. And it does that across its entire plant, and everything can be balanced and managed from the central controller very conveniently. Moving to a voltage source with grid forming controls, suddenly the PPC has to manage much more dynamic entities. It still has to make sure that all of these inverters combined provide what the grid requires and what your contract requires at the point of interconnection, versus what the inverters are actually doing at their low voltage connection themselves. So there's a lot of coordination going on there. Black start capability. Yes, maybe an inverter can act as a voltage source and it can ramp the voltage up nicely, so we avoid some inrush initially. But that's just one inverter. In order to black start a significant portion of the grid, we need many of these inverters. So how do you coordinate all of those together uh, across a fairly complex topology of your balance of plant? And then how do you continue to coordinate that as the grid becomes more and more restored? So the point of this plot here, I've labeled it qualitative, is to just reiterate the fact that grid forming controls, they're still being developed. Different suppliers have different strengths and weaknesses on their grid forming side. But on top of that, overlaid on that is the dark blue line. So that's when you combine the grid forming controls of a PCS with specifically tuned plant level controls, considering the grid forming, then you actually have a much broader, a more fulfilled capability from your plant. Getting mindful of question time, so I'll try to skirt through some of these. Black start, I mentioned coordinating multiple inverters together, performing a voltage ramp, not just from one, but from all. One of the requirements from the VDE code here in Germany is that uh, for a high voltage black start application, you actually have to be able to ramp the voltage up over 10 minutes. So this isn't then just about avoiding some initial inrush from transformers, but it's really for a system operator when they try to restore their grid. It's a very stressful situation. There's a lot of things going on. As they start to bring voltage back up, they might see down the line with less load or with a distribution transformer tapped in a certain way, they might start to see an overvoltage down the line. To buy themselves some more time to react to such a situation, they require that actually we do a very slow ramp, so not just to avoid inrush, but really slow so that they can react better. Um, droop versus inertia. When we're on grid, providing the grid forming inertia, responding to Rock-off events, the inertial control mode is good, but it's only reacting to the change of the frequency, not the absolute deviation. So in islanded situations and black start situations, generally the best control scheme that we've found is droop. So comparing these two modes, knowing when to use them, when not, am I in an island or not, that's another role of the plant control. Power oscillation damping, grid forming controls inherently provide damping to the system, but the plant level controller can modulate the response and provide even more oscillation damping. And then I'll stop on this slide to ramp it up. Uh, a lot of what we've been doing over the years and what everyone in the industry has been doing over the years is kind of figuring out, getting comfortable with these new controls. There's a give and take from the OEMs and from the grid codes and the developers, but in order to continue to drive the energy transition and to actually bring some of these capabilities up to scale, we need more standards. We need to streamline this. It can't be that everyone's doing their own validation based on what they think is best. We need component level standards. That's not just for the PCS component, but also for a plant level control. We have Anlagenzertifikat in Germany, the Einheitszertifikatanlage, ETA, specifically for plant controls. Some other countries also have plant control specific requirements. We need to look at pro-islanding clauses. It's a sensitive subject, of course. DSOs, they're used to anti-islanding, and they know that in critical situations they can rely on renewables to disconnect from the grid, which allows a safer operation of their system. But moving forward, everyone can't disconnect from the grid, so we need to discuss that and figure out what is the best balance there. We need to standardize the anatomy of short circuit from a PCS. There's a lot of great standards out there, and just physics and all of the textbooks on the short circuit provision from a synchronous machine, right? But from a grid forming power electronic device, it can be sort of whatever you want. In order to turn that from a Wild West into sort of a more civilized society, we need a code of conduct, and we need to tell people how they should behave. There's many other aspects here under component standards, also under grid codes. But I think I do want to get to some questions, and so I don't know, Julia, if it's okay for you, I'd like to open up for the Slido questions.
Yeah, sure. And thank you, Ben, for leaving time for questions. We have quite a few. So, I mean, funny enough, we were just talking about it before we started the webinar, that there will certainly be a question about costs. So the first and the most popular question is, what's the cost difference between grid following and grid forming in terms of percentage?
Mm-hmm. It's not an easy question, right? A straight percentage, I'm not going to give you, not just because I'm trying to be coy, but because, as always, it depends. I had the slide with all of the different applications, the additional controls and balance of plant considerations that you would have to price in for a project in Australia versus a project in the UK are going to be totally different. I think what I could say, and I think is something that does need to be more openly discussed, is the areas where more costs can come in. So from the beginning, if you're an inverter manufacturer, you've had to develop these controls, you've had to test and validate them on yourself, and with these new controls, you also have to figure out a way to market those and sell those and support those. So what we see from our OEM suppliers is that they put a cost adder on the controls themselves. The derating that I mentioned, some suppliers they don't give you the same power in grid forming as grid following, so right away that instantly forces you to overbuild, and that's not even the trade-off. Overbuilding to unlock additional fault current or inertia power. Even before you get there, some suppliers are already forcing you to overbuild on their inverter hardware. Balance of plant, what I was talking about with metering, or if it's a Black Star project with UPS and hardening your controls infrastructure, and then testing, validation. If we still don't have component standards, all of the testing falls back on the project developer, the solution provider. You have to do much more testing and validation up front, as I showed you what Fluence is doing. The customer is then interested, for the national grid projects, we have extra tests proving the capability. Then on site, you have extra tests. When it comes to the service phase, inevitably some new behaviors will come up, and it's going to be more complex to really analyze those issues and service those. And the final additional cost component, I would say, is just the cost of capital. If you can get the same return from a battery that's doing grid following services, which I've called a couple of times old or traditional, your business team probably feels much more comfortable with that than some new market where how long is this service really going to be there? Is it paid now, but later it's just going to be compelled, so I'm not going to get paid for it later? Those are the main additional cost buckets, and hopefully that explains why it's not so easy to just put a percentage on it.
Yeah, thank you, Ben. I appreciate. Maybe one follow-up question. I'm still, interested, and if like covering all of these considerations that you were talking about, you had to put in kind of a ballpark percentage number from like the lowest difference to the highest difference that you may see in terms of like total costs of the project. what would that range look like?
I don't even think I would feel comfortable putting a ballpark number on it. I think that starts to get out of my lane. I'm the controls engineer doing the technical sizing. I can say that, of course, there's a team of commercial people at Fluence that if you want to know more, we can get you in touch with them.
Sounds good. So the next question is, do you have any suggestions or ideas of how to evaluate grid forming IBR contribution to system strengths, something other than short circuit current contribution? So you mentioned, say, in Australia, there is like this consideration of deterioration of system strengths from an IBR resource that connects. But do you have any ideas for how to value grid forming plants' contribution to system strengths?
Mm-hmm. So I think even just the short circuit ratio that I've hit on a couple of times, there's also different variants of short circuit ratio. You'll see maybe equivalent short circuit ratio, or there's different methods for calculating it. I've seen talk, and even myself years ago on isolated systems, sort of talking about a reactive inertia, almost just to kind of draw that parallel to the inertia on frequency. Voltage stiffness, as I've mentioned here. I think there's a lot of papers. I don't know if I would necessarily advocate for one or the other. Short circuit ratio is definitely a bit of a static measure. You have short circuit level, as they've used in the UK, but that gets more at the actual fault current and not necessarily how you're dynamically stabilizing the voltage sort of in a small signal sense. You can easily calculate it, and they have a line saying based on your voltage drop, how much short circuit level should you provide. I don't think I can give one value. That's more on the TSOs or the ISOs to define, but I definitely would say that we should get probably a little bit more advanced than short circuit ratio, something a little bit more dynamic. If you're an isolated system where it's not just about the stability of the voltage, but really coming down to the nuts and bolts of, can this battery trip my protection settings, then actually you're totally away from short circuit ratio, and you're just looking at, again, the SCL that the UK used, or in our isolated island projects in the Azores or on Madeira. That's then a small enough system where this battery, especially when other thermal generation is off, it has to provide a certain amount of fault current to reliably trip protection, and not just a nice bolted three-phase fault, but also harder to detect single-phase faults.
Thank you. Sounds good. So the next question is, any thoughts on how to counteract bad grid forming requirements, such as nonlinear behavior like dead bands, expected, it says GFL fast PQ step response, but maybe they meant GFM, not sure. So I guess like the way I'm reading this question is how to counteract bad grid forming requirements that are kind of hard to conform with.
Mm-hmm. So based on the responses we've seen from tests from different suppliers, um, I don't want to say that people are gaming the requirements, but anytime you set a target, there will be some people that say, okay, I'm going to jump up and I hit that target at the certain time. Others could say, oh, I do nothing, and then in the last moment I hit up, and someone could be somewhere in the middle. So I think we have to be very precise in the way we define these capabilities, not just saying, okay, this is the magnitude of the short circuit level, but actually how to get there. And there's a good example from National Grid, sort of in the process of the tender, and just in general, National Grid has been very good about, okay, we started to define it, but we've realized that there might be a bit of a gap here. So we release a new document which provides more guidance. AMO has done this, FinGrid is doing it. I mean, I think everyone is doing it, and it's nice. It sort of shows like a humble side. Okay, maybe we didn't get it right, but we know we need to get it right, so we're going to keep revising until we do. Um, so yeah, I would say because it's a very transient and dynamic capability, your requirement also has to be equally transient and dynamic. What we're
Yeah,
seeing
more
from
iterative, right?
more iterative, and also you know, not just saying, okay, this is the magnitude, but defining the rise time, the reaction time. You mentioned part of the question was grid following. I think in general, a lot of codes have adopted this uh, response within 5 seconds or reaction within not 5 seconds, 5 milliseconds, and this is, I would say, largely to kind of kick out grid following. That's one way to really say, okay, maybe some very fast, low-level grid following could still do it in less than 5 milliseconds. But you know what we need is the immediate response, which would come from the physics of a synchronous machine. So if you can show voltage event here, and within 5 milliseconds or even earlier, I see a change in your current, great. That means you're grid forming. That's at least kind of the first hurdle. We also see this loss of last synchronous generator test, which also kind of gets at teasing out, okay, is this really grid forming or not? And then I think what NREL has put a lot of ink on paper about their impedance scans, uh, showing the stability of the controller as well, and sort of kind of characterizing the response from grid forming versus grid following. I haven't seen anything exactly quantifying really what limits would be passable and not. Um, but maybe those are a couple of ideas. Hopefully it helps to answer the question.
Sounds good. We are running up on time, but I'll ask this one last question because I think that's on many people's minds. Do you see any downside of mandating grid forming for all future battery energy storage?
I think I think there are potential downsides, in particular because coming back to the requirements and how it's required. Um, so if you just kind of say, let's say right now, someone just said, okay, everyone be grid forming in the next 6 months. Of course, there's going to be a lot of scrambling. There's not yet the maturity on component standards and grid codes for us to all reliably provide solutions that are actually on equal footing with each other. Um, I think everyone would be putting in an honest effort, but nonetheless, you would have a huge disparity in what people were actually providing. So one downside, particularly now, before you have that maturity in your standards and your codes, is that you don't actually know what you're going to get, right? Uh, Another downside would be if you're going to just flat out compel it for everyone. That means that you also need to say, you also need to compel a certain amount of overbuild. So either you take more of the AMO approach that says, look, if you do it, great, but as you reach your nominal power, those sort of grid forming capabilities like inertia or fault current, you're allowed to derate those as you get to full operation.
Mhm.
That is one way to do it, but if you only do that, then it means when all of your plants are at or near full power, the actual amount of grid forming capability you have is not really there. So if you are compelling it, requiring it because you want those capabilities to be there all the time, then you also need to specify how much on top of the business as usual needs to be designed in. And once you start doing that, you're going to have people overbuilding in areas where you don't actually need it. You know, there are parts of our grid that still remain quite strong, especially in a voltage sense. So I, I think it's kind of a blunt approach. Um, I think it is quite a it is quite a pressing topic, especially in certain networks where they have to push people quickly. Um, but my concern there would be that yeah, it's too blunt and the codes just aren't ready yet.
Mhm. Yeah, one of the analogies I'm kind of thinking about in that respect is like primary frequency response, so that you're requiring all resources to have capability, but for a certain number of resources, maybe you have a market to actually have this capability available at all times, right? So this way you have it spread around bigger pool of resources and not all of them hitting limits at the same time. But when they are, you also have this additional reserve, quote unquote, that you can tap into.
Yep. Good
All
analogy.
right, so we are on the top of the hour, and we need to wrap up. Ben, I would like to thank you once again for this really informative presentation, and the audience for your attention and great questions. As I mentioned earlier, the email will go out once the video has been posted, and we will answer all of the unanswered questions offline. So Ben will ask you to do that. And then we'll get them posted as quickly as possible. Our next webinar is from the ESIG webinar series and will be on Atlantic Offshore Wind Transmission Study by NREL on June 6 at 4 p.m. Eastern Time. And more details, including registration, will be available at ESIG event page shortly. I would also like to cordially invite you to attend our upcoming ESIG Forecasting and Markets workshop on June 11th through June 13th in Salt Lake City in Utah. And any further information on all of our webinars and meetings can be found at our website at www.esig.energy under events, in our newsletters and informational emails, and you are all invited to attend. Ben, thanks once again for your presentation and for joining us at probably late hour for you right now. Thank you all for your interest. We look forward to seeing you again in our webinars and other events. And in the meantime, take care, stay safe, and thanks so much for your participation. See you soon.
Thanks so much, everyone. Good night, good day, good morning. Bye-bye.
Bye.